Hi, I'm Michael, and I'll be covering CPM sections 10.1.1 and 10.1.2 today, which goes over a series, whether they converge or diverge, and two tests you can use to determine convergence or divergence. The first being the divergence test, and the second one being the geometric series test. So a series is essentially the sum of the terms in a sequence. You know what a sequence is. You have this sequence here. It happens to be an alternating sequence, 1 minus 1 half plus 1/3, and so on. So a series is just a sum of all these terms. You can write a series in shorthand with sigma notation. You've seen sigma notation in your previous math classes before, and um, and yeah, so we're interested in knowing whether the infinite series converges, adds up to a finite number, or if it diverges, which means it grows without bound and it doesn't converge to a finite number. So the question we want to know is, do the partial sums converge or diverge? The partial sums just being the sum of part of a sequence, as you can see down here. So as I said before, convergent series, in convergent series, the partial sums approach a finite value as n approaches infinity. In divergent series, this does not happen. Instead, the partial sums do not approach a finite value. So maybe they go to infinity or negative infinity, for example. This is an example of a convergent series. As you can see, the series converges towards zero as n gets larger. This is a divergent series where the series seems to go towards infinity as n gets larger. So the first test I'm going to cover is called the divergence test, also known as the nth term test. And what it states is that for some series S equals this thing in sigma notation, it just means an infinite series where the argument is a of k. So that's going to be your, 1 over n or n over n plus 1, whatever series is in there. You're going to take the limit of that as n approaches infinity of the argument, and if it does not equal 0 or it doesn't exist, so as long as it's anything other than 0, then the series itself is going to diverge. That's basically the divergence test. If if the limit equals 0, this is important. The test is inconclusive, so you have to use another convergence test covered in later chapters to test the series. So this is just kind of restating what I said. And now we'll move on to an example. So let's take a look at this series, n over n plus 1. So does it converge or diverge? And if it can, and what's the reasoning behind whether it converges or diverges? Feel free to pause the video. Okay. So first of all, you're going to find the limit as n approaches infinity of this thing inside of the sigma notation. So the limit as n approaches infinity of n over n plus 1, as n gets infinitely large, you're going to have an infinitely large number over an infinitely large number. Infinity over infinity is just 1. And since 1 is not 0, the series is going to diverge by the divergence test. So now I'm going to cover a common pitfall that a lot of people fall into with the divergence test. Um, I've seen this a lot, and basically what happens is some students and I have personal experience think the series must converge if the limit equals 0. But that's not true. What is true is that if the limit equals 0, it's a necessary condition for convergence, but it's not a sufficient one for convergence. In other words, if the limit equals 0, the series may or may not converge. It can diverge, but it can also converge, depending on what the series is. So let's look at an example, right? you have the harmonic series. If you don't know what that is, that's just 1 over n. So 1 plus 1/2 plus 1/3 plus 1/4, so on. So the limit as n approaches infinity of the harmonic series, right? 1 over a really large number is 0. Even though it by the divergence test, the series is inconclusive, it still diverges. In the way you know that is by the p-series test, which will be covered later on. So keep this in mind. If the divergence test doesn't work on a series, you have to use another test. Don't just say by the don't say something like by the divergence test the limit equals 0, therefore it converges. Don't say that. All right, we're halfway there. So just hang in there. All right, the second half of today's lesson is going to be about geometric series and the geometric series test. So geometric series, right, is a series that sums a sequence and it has a common ratio of r. So you're multiplying each successive term by that same r. As you can see here, a geometric series is just a plus ar plus ar squared and so on. Each term has a common ratio multiplied on it. And the test to determine whether a geometric series converges or diverges is, I think it's the most simple test and it's the most straightforward. And what it is the series is gonna if the absolute value of r, is less than 1. In other words, if r is between -1 and 1, then the series is gonna converge. Otherwise, it's gonna diverge. So this might help you visualize what that means. If the common ratio is anywhere between -1 and 1, not inclusive, then it will converge. Otherwise, it will diverge. Also, one other thing that's important is the sum of a geometric series test. The sum of a geometric series is a which is the first term, all over 1 minus r. I know you can't see it here because it got cut off, but r is the common ratio. So a, the first term, over 1 minus r, the common ratio. So that's the sum of a geometric series if it converges. All right, now let's look at a couple of examples. So determine if this following series converges or not. And if it converges, determine its sum. Feel free to pause the video and write down your answer if you so wish. All right, so what do we know? We know that a equals 5 and that r equals 2/3. And based on that, is less than is 2/3, which is less than 1, so it converges, which is correct. But hold on, let's stop there. You want to make sure to never use the word it when describing a function, an equation, a series, or anything. Don't say it to describe f of x or g of x or any series or any equation. Just don't. You have to be specific. You might on an FRQ, you're gonna lose points if you use the word it. So don't use the word it. Instead, use the word for example, the series, or write out the series out. Just don't use the word it. You have to be specific. So you can say the series converges. So now that we know the series converges, let's find the sum. The sum is a over 1 minus r. Plug in a and r, and you get 15. All right, let's do one more example of geometric series. So does this series converge? And if so, what's the sum? Feel free to pause. So since r is 1.1, we know that it's greater than 1. R is greater than 1, so therefore the series diverges and it does not have a finite sum. All right, finally, let's take a look at a check for understanding quiz. So how this is going to work is I'll display 4 series up on the screen, and you're going to have to determine which of them converge. Here they are. Again, feel free to pause. All right, so looking at each individual series, the first series, right, it's 2n minus 1 over 2n. And just taking the limit as n approaches infinity of this thing, as n gets extremely large, then minus 1 is not going to matter. So you're just going to have 2 over 2, which is just 1. And because 1 does not equal 0, 1 is going to diverge. All right, number 2 is a geometric series. R is 1/3, which is less than 1. So therefore, this series is going to converge. All right, number 3, you have this scary looking kind of quartic series, but if you break it down, it's actually pretty simple. If you take the limit as n approaches infinity, right, of this thing, this monstrosity, uh, look at the largest term of the numerator. It's n to the 4. Versus if you look at the largest term of the denominator, n to the power of 3, it's n to the power of 3 to the times 3/4, right? 3 times 3/4 is 9/4. And 9/4 is less than 4. So by that logic, the largest term on the numerator is going to be a greater power than the one on the denominator, right? So therefore, the series is going to diverge because n is going to get extremely, extremely large as n approaches infinity. And finally, we have number 4. So this is another geometric series, and r is negative 5/6. And if you take the absolute value, that is less than 1. So therefore, the series converges by the geometric series tests. So your answer is going to be number 2 and number 4. All right, to wrap things up, remember that a series is the sum of a sequence. And there's two ways that I went over about how to determine whether a series converges or diverges. There's other ways, but these are the two, I think, most simple ones, the ones that are covered first in the CPM textbook. So you have the divergence test. If the limit does not equal 0, the series diverges. And then you have the geometric series test. So again, if absolute value of r is less than 1, the series converges. The sum is a over 1 minus r. Otherwise, it diverges. All right, that's it. Thank you for watching. I hope that helped. And yeah, that's it.